Can you hear me now? Okay. Are we ready to go? Okay. Thank you, Maureen, and thank everybody for returning this week. It's the second class of this March program. Last week we focused on what happened in the distant past. Next week we're looking towards the future, and today we'll be looking at the things in the present and the recent past. Okay, again, last week we noted that there has been a lot of interest in astronomy for thousands of years in many of the cultures. I gave a few examples of some of the cultures. It was not exclusive. For example, the Islamic culture, other cultures were doing astronomical observations during the last couple of millennia. We also saw that the sun-centered model, a heliocentric model, was supported by data, and a model was constructed by Kepler using Brahe's data. The result was that the orbits were elliptical, at least in the model orbits were elliptical. Of course, the orbits are not exactly elliptical because the planets are affected by neighboring planets and by moons and so forth. So a good model for the orbits of the planets of the solar system, which is of various eccentricities. What I hadn't realized is that how Kepler actually did this. He used the data, but used triangulation to determine points on the Mars orbit. It turns out that if he'd used any other planet besides Mars for his study, he would have found that the orbits were consistent with circular orbits. That is, ellipses with very, very low eccentricity, which is fortunate he used Mars, because then we realized that the orbits were in fact ellipses, and the orbits of the other planets besides Mars were very close to circles, but they weren't exactly circles. Today we'll be looking at mostly the missions to Mars, but we'll begin with a look at Mars moons. These moons were discovered in the 1800s, and so there's some very interesting things about Mars moons that is actually related to our own moon. Most of the time we'll be looking at the missions to Mars. The basic objectives were a search for life, an understanding of the surface features and the geology, that is the interior of Mars, as well as the surface features. And probably we'll have to wait till next week, maybe we can fit it in later today, is a study of our understanding of the atmosphere and the climate of Mars. In the late 1800s, Schiaparelli, looking through a telescope, a very famous astronomer, and he saw these lines or bands or some structures on Mars, and he called them canali. Of course, canali means channels, which are naturally made paths, but some people interpret them to mean canals, which are made by intelligent beings, human beings, and this caused a great deal of confusion for several years. Schiaparelli was fairly well known, in fact, so well known that in the movie The Martian, the place where the Martian left in an attempt to go back to Earth is called the Schiaparelli crater. So the name has stuck on Mars. Now, Mars has it's been discovered that Mars has two small moons, much, much smaller than the Earth's moons. These were, they were named, Deimos and Phobos, they're named for the sons of Mars. I think they're twin sons of Mars. They're very, very close to the Mars surface. In fact, so close that it's very difficult to discover them. Not only are they small, also very close to Mars surface, and they're hidden in the glare of Mars. Paul trying to find moons on Mars. After all, we already knew that the Earth has a moon and Jupiter has at least 4 moons. He had a lot of trouble, but his wife urged him to continue on. And then the next night he was able to find Deimos, and a little bit later, he was able to find Phobos. The diameters are they're really tiny. They're about 10 and 20 kilometers in diameter. That's about 1/1000th of the size of Mars, and much, much smaller than our own moon, and much smaller than the moons that Galileo had discovered on Jupiter. There's some debate as to where these came from. They're so close to Mars, it's very unlikely that they could form in the same way that Mars formed. And so people think that either they're captured asteroids, after all, Mars is at the edge of the asteroid belt, or that could be the result of a collision, a collision with Mars or a collision with some other asteroids. Now, the United States had actually, NASA had planned at one point to send a mission to look at these moons, but instead the mission was changed to going to an asteroid and trying to see what an asteroid looked like. So that was canceled. But Japan does plan to go to explore both of those in a few years. So we'll see. The moon is so small that there's virtually no gravity, and so and also there's some sort of safety issues associated with going to planets. So you have to be very, very careful. Now the moons on Mars, it's on the left in the red font. Phobos is the larger moon, is moving gradually closer to Mars. Now it's already very close to Mars, and of course Mars gravity is attracting it. The tidal forces associated with the attraction break up the moon. It did form
May I interrupt for a second? Pardon me. Somebody doesn't have their mute on. Beth, maybe that's you, George. If you would put your mute on so I can hear. I'm sorry to have to say that. Thank you and goodbye.
Okay, thanks for your help. So it might break up, and where it breaks up, as it's moving around Mars, it could actually form a ring, not unlike the rings that we see in some of the other solar system planets. We know that Saturn certainly has rings, as does Uranus and Jupiter. And so already people can see the moon starting to break up, see some cracks already showing in the surface. Well, the right half of this slide actually talks about the Earth's moon. And although it's not really Mars, I just find it very interesting. It turns out that the Earth's moon is not moving towards the Earth, thank goodness, as is Mars' moon. In fact, the moon used to be very close to the Earth, and it's been moving away for billions of years. Moving away right now at a very slow rate, and they estimate around moving away around 4 centimeters a year. That's 25,000 miles per billion years. So we don't have to worry about it disappearing anytime soon. Of course, when it moves significantly further from the Earth than it does now, we will lose that nice solar eclipse where the moon and the sun have essentially the same apparent size, where the moon can sort of it's the same size as the apparent size as the sun. But as the moon moves further away, then the apparent size of the moon would then get smaller, and we would not see a total eclipse like we do now. We'd see more like a ring of fire around a black moon. Now, why is the Earth's moon moving away? Well, the Earth has oceans, and the moon's gravity, of course, produces tides. That's something that we are very aware of. And the gravity produces a bulge in the ocean, order of meters high. That's not a huge amount. And this bulge moves around with the rest of the Earth, and then sort of leaves the moon behind. But as the bulge moves ahead, the bulge pulls on the moon through the gravity. It's not a huge amount of gravity. It's just water meters in height, and so it pulls on the moon. But then as it moves ahead of the moon, because the the bulge is moving at, one rotation, around the Earth per day, whereas the moon takes more like 29 days to move around the Earth. So the bulge that moves ahead of the moon and then pulls on the moon very gradually. In so doing, the bulge then increases the energy of the moon, and this energy is then used to raise the moon slightly further away from the Earth at the rate of 4 centimeters per year. And this energy can only come from one place. It has to come from the Earth, in fact, the Earth's rotation. And the result is that the Earth has been spinning slower and slower as time progresses. 400 million years ago, when animals went from the ocean to the dry land, the moon was much closer to the Earth. As a result, there were much stronger tides. And this had a very crucial effect on evolution. If the tides are bigger, that can affect the transition of animals from the ocean to the land. This is very important in biology, and has really nothing to do with Mars, but I just find it interesting. I'm just having trouble moving my my slides. Okay. Now we're going to move away from the 1800s into the second half of the 20th century, where we started doing some exploration of Mars. Of course, people were taking images of Mars and looking at them through telescopes and so forth. And the exploration of Mars had several scientific goals, as well as political goals, I guess. Because one is that we're trying to determine whether or not life ever arose on Mars, what exists on Mars now, or was ever on Mars. We're trying to understand the climate of Mars. We're trying to understand the geology of Mars, the surface geology, as well as the interior geology, and perhaps prepare for human exploration. These are the basic scientific goals for the exploration of Mars in the last 60 years. One of the leaders in this endeavor is Carl Sagan. Most of us know him from Cosmos, and a very prominent scientist. Unfortunately, he died in 1996, 24 years ago. A friend of mine, so I miss working with him. His main contribution, one of his main contributions, was explaining science to the public. Extremely good speaker, extremely dynamic person in professional meetings as well. He was the director at Cornell University. He actually instigated the idea of sending records on the Voyager spacecraft, which basically went on a tour of the planets. It didn't actually go around Mars or land on Mars. And on this, and it was supposed to be a record of what human beings are like on Earth, and it had music, stories, and so forth. Hopefully, people could understand the music in the English. One of the famous stories is that someone sent a message that was supposed to have been coming from one of the people on other planets, and the message said, "Please send more." Oh gosh, I forgot the guy's name. I'm blanking it now. Okay, anyway, he wrote many books. Some books were in biology. Other books were in planetary science. He was the editor of the journal Icarus. That's in planetary science, the American Astronomical Society, and the Division of Planetary Sciences. And he contributed greatly to NASA's Viking explorations of Mars. In the past 60 years, there have been many attempts to go to Mars, various missions. I counted 43, and 23 were failures, 20 were successes, so the successes were almost 50%. And of these successes, Some of them were flybys, that is, that the spacecraft would just kind of go towards Mars, go around Mars, and go off someplace else. And later, these were orbiters, that is, they would go to Mars and they would go circle around Mars, taking pictures, doing other types of data gathering through instruments. And 8 of them actually landed on Mars. Those are the most recent ones. Some of the discovery of Mars in the last 60 years were that discovered that liquid water could exist. In fact, people are virtually certain that there is a significant amount of liquid water on Mars. Mars is interacting with the magma, that is the material that's coming out of the volcanoes on Mars. People think that Mars was suitable for habitation for millions of years. They haven't actually found anybody up there yet, or even any live object, any plants or animals. Mars could have been habitable in the past. In the past, the Mars had water. It was significantly warmer than it is now. And they found the existence of key chemicals that we view on Earth as being necessary for life. They noticed some ripples on the plains, and it looked like what we would see just from floods and from rivers. And that might have happened when Mars' spin axis was much different than it is now. The tilt of Mars is almost the same as the tilt from on Earth. That means that Mars has seasons, not the same temperature, but has seasons very much like we have here on Earth. They also noticed that there are dust devils. A dust devil looks like a baby tornado, much safer, and they discovered the frequency and the dynamics of these dust devils that are moved by wind in this very thin atmosphere. So that allows them to try to understand where all the dust comes from and how it's maintained in the atmosphere. Okay, the first group of missions were just orbital missions by Mariner. You can see that these occurred in over a 7-year period in the late 60s to early 70s, about the same time as we were sending men to the moon. All these Mariner missions were orbital. None of them actually landed on Mars. From the orbits, taking pictures, they did not see any signs of life. They did notice and measured some massive topographical variations where the height of the volcanoes and the mountains were several times as high as the corresponding ones on Earth. They're able to determine that the atmosphere is carbon dioxide. They probably already knew that. They already were able to measure attempt to find the magnetic field. They couldn't find the magnetic field. If there is any, it has to be very weak. And that can be a problem since magnetic fields are very useful in warding off solar radiation that could be harmful to life. Fortunately, the Earth has a magnetic field that protects us. Mars is a little bit further away, but still there could be some radiation problems on Mars. We'll talk about this probably next week. They did not see any channels or canals, but they did notice that there could have been water in the past. They did notice the polar ice caps. They weren't able to determine whether they were made out of it by Mars. And one of the major things they noticed was the major dust storms on Mars. That's very easy to determine because in a major dust storm, the details of the viewing of the entire planet kind of gets washed out by major dust storms. Yeah, this was known in the Mariner missions even before they landed on Mars. Okay, the first landers on Mars were the Viking landers, Viking 1 and 2 in 1976. These were launched a matter of weeks apart in 1975. And the idea was for them to get to Mars on July 4th, 1976, which of course is the United States bicentennial day. Unfortunately, the Viking 1 mission was delayed. I was actually at the proposed launch, and I came back from the Cape sort of disappointed, but eventually it got off there and went up to Mars, landed on Mars. stayed put. It wasn't a rover, it just stayed put and sort of scratched the surface, dug into the ground, did some other scientific measurements, and collected data for 6 years. Now, the design was only for 90 days, so it actually lasted, as most of these landers did, actually lasted a lot longer than the very conservative design criteria. I don't know if anybody's interested in actually looking at the scientific results, but here is a reference. It's the Journal of Geophysical Research at JGR, volume 82, number 28 in 1977. That's a year after the Vikings started collecting the data. Because probably the biggest question for citizens in the world is there life on Mars? And so Dr. Levin in 1952 came up with a test to determine whether or not there could be the determination of any microbes on Mars. And this was used in the Viking missions. And I guess scientists like to have some fun too. They call it Gulliver because they're looking for all these little Lilliputians, microorganisms on the planet. Later it was called a labeled release, which is more of a scientific name. And what the idea was that you would check for the release of radioactive gas. You squirt a little bit of radioactive food onto the soil, hoping that microorganisms will metabolize it and then kind of breathe out, whatever they do, some radioactive gas. And if so, then they had an instrument on the landers, and the Viking landers, to determine whether or not any of this breathed out the gas by the microorganisms was radioactive. It turned out that they did not detect any radioactivity that was as a result of this process, this label release process. And as a result, it was determined that there was no evidence of living microorganisms, at least at the Viking sites. Because that doesn't mean there's no life, doesn't mean there's not microorganisms someplace else, but since the lander was not moving, it was not a rover, that's about all they could tell. After the Viking missions, there were a sequence of Mars rovers, that is, there were landers, and the landers carried with it a small rover. I don't know whether it's think of a golf cart, maybe the easy way to think about it. And it was released, then it was able to move very slowly along the Martian surface. You have to be careful with some of these names. The lander has a name. For example, Pathfinder was the first one. And the rover had a different name. It's called Sojourner. And so when people are talking about the opportunity, you have to remember, is that the rover or is that the lander? And I'll be talking almost always about the rovers right now. So anything I mention except for this Pathfinder is a rover, and is a map on Mars indicating where these landed. You can see the Viking one is near the North Pole. Pathfinder is a little bit further south and east of that. And Opportunity rover started, well, it's at the equator. It didn't move all that far. It moved a matter of maybe tens of miles. It didn't zip around the planet. It moved very, very slowly. Now the Sojourner, the rover, worked for a few months. Mostly this was a test of a concept and getting a little bit of practice. And so the rover was actually very small. It worked for a few months. So now NASA learned how to do this. And so the other rovers were significantly larger, had a lot more scientific equipment on it. The Spirit got to Mars in 2004. Opportunity got there about the same time, a matter of a few months difference of when they landed on Mars. Just like the Vikings, the two of them landed very close together in time. These two, Spirit and Opportunity, landed together in time, months apart. Now, Spirit did very well for about 6 years, and then it ran into some technical problems, and it was lost in 2010. Opportunity lasted at least 14 years. Then a dust storm came over the planet. The dust covered the solar panels. That just cut off the energy source, since the sunlight did not get through the dust, and so the opportunity just kind of sat there in suspended animation. Now, eventually NASA gave up on it. So I don't know if it's still running or not, but 14 years is not bad for a very early attempt at trying to study a planet. The most recent one that was landed in 2012 is still working. It's called Curiosity, and we'll be looking at some results of these and as we progress in the next few minutes. Because the Opportunity rover, that's one of the two that landed close to each other. This is the one that lasted the longest. Kind of, I wouldn't say zipped around Mars, kind of strolled around Mars, and actually covered, I don't know, maybe 40 or 50 miles over the 14 years. That's not really all that fast. It took a huge number of pictures, almost 250,000 pictures. It analyzed the atmosphere, get some really good atmospheric data. As I went around searching, well, I hate to, it's not really like Lewis and Clark, but it could keep wandering around just looking at stuff and discovering things, and was able to find some clues to the existence of water in the past. And there's a bunch of discoveries, and hopefully I can find it. Okay, this is not a video. This is just a PowerPoint that I just copied from the web. This is one scientist's idea of what the top 10 discoveries of Spirit and Opportunity. Those are the rovers that landed around the same time when it was 15 years ago, 16 years ago, whenever it was. One of the things that they discovered is that not only does Mars have carbon dioxide, because 95+% of the atmosphere is carbon dioxide with trace amounts of other things, including argon. They discovered some argon, and how important that is, but it's something they found. Another thing they found was Martian dust devils. Now, Mars has massive sandstorms, but also has dust devils. Dust devils look like, as I said before, baby tornado. You can probably see it at the top center of that picture. They saw some dust devils, and they were able to determine, what conditions are appropriate for dust devils there. We also see dust devils in the deserts and on Earth. Also, these rovers were able to look at some details of the ground, the soil on Mars. One of the craters indicates that there's some interaction or effect that water and frost may have on the land. So that's another discovery that was made. Discovered some buried water. on Mars. They saw water interacting with the dust, also interacting with rocks. They saw water interacting with the magma from the volcanoes. They also noticed some wind-blown ripples on the plains, and because this is just a dust on Mars, a sand on Mars, that is being blown around by the Martian winds. It's also discovered some meteorites. In fact, one of the meteorites, not this one, actually is known to go from Mars, get kind of blown away from Mars, and eventually landed on Earth. Here's one of the Mars meteorites that actually was found on Mars. Here's a very important one. They discovered that there is very little evidence or likely that there was a habitable environment long ago. This is the big question: is there life on Mars? Was there ever life on Mars? Well, we don't know if there actually was life on it, but it's an environment that certainly would have supported a life a long time ago. I think it's the last one. They found some evidence of ancient acidic lakes a long time ago, the lakes that had some acids that were affecting the formation of some of the landforms on Mars. And I think that's the last one. Yeah. Yeah, they've found some lake beds that suggest the existence of water in the past. Also, the chemistry that they did some chemical experiments suggests that there's a possibility of having microbes in the past. They couldn't find any now, and as I mentioned before, I hope this works. Now, one of the websites actually contains what it would look like from Curiosity's cameras as it moved around, and we'll see if I can get to that. There you can see Curiosity just moving around and just checking the scene, see what things look like as it moves around. This is the front camera. There's a lot of cameras on board. There's the camera in the front as you can see it moving. As it's turning, it's looking to the left. There's another camera that they can be moved. This shows the how the rovers were able to collect data. They had a bunch of cameras. This one is on the arms. They can move up and down, and it has a pivot. Other camera is in front. You can see where it's going, and also the rover can actually move around. So this is what was happening when the rovers were being used. They didn't just kind of go in a straight line looking dead ahead. They actually had instruments on board that could look left and right and move the cameras around. Because one of the though to move the camera, you need some instructions, messages from Earth, but it takes quite a while for messages to get up there. So all of this was happening pretty slowly. Here's a picture that was taken by the orbiter, not by the not by the lander, and it shows a picture. And the interesting about the picture is you see these. It's on a slope. You can see some streaks on the slope. The hypothesis is that these streaks are caused by water just flowing down and sort of washing away as whatever was on top, whatever was on top of that slope. Now they determined that the water must have been extremely salty. It's brine. And so that's some more information. The water wasn't just pure water like we have in lakes or even in the ocean. It's very, very salty water, at least at this place. Okay, I guess we've been going for about 30, 35 minutes, and it's about time for a break. And it's gonna be an 8-minute break. You get something to eat, you go to the restroom, just sit and listen to the music, whatever you want to do. Send some questions and comments on your to me, and now this is playing the music. Where is it now? Yeah, and some of you have been to Boston, and this is at the Prudential Center in Boston, and it's called a flash mob. You'll see it. So see you in about 6 minutes. That's one of my favorite pieces. Again, it's by Holst. We saw the movement of corresponding to movement number one, which is Mars. This is Jupiter, much different of what Jupiter is. Anyway. Okay, we have another couple minutes and I'll get back. Okay, hello again. I guess it's about time for us to get going for the second half of today's class. I did get a few messages from people. Most of them were telling people to please mute. One asked, how do we know that water is so salty? That's a good question. And my answer to this, I don't know. They had a lot of instruments in that Mars mission, and I don't know to what extent they could determine remotely the salt content. I also asked the people who are in charge of these experiments and teams, since these experiments lasted over, 15 to 16 years, did they have more than one team? Again, I'll plead my ignorance on that also. I don't know if they had the same team or whether somebody dropped out of team and someone else joined. I really don't know. Great questions, crummy answers. Okay, for the second part of today's lesson, it lasts about 30 minutes. And look at some of the geology. Well, I'm not a geologist. My background is in fluid dynamics and mathematics and physics. So I'll do the best I can with the geology. Now, there are some surface features that tourists could explore, because done so tongue in cheek. These are surface features that are interesting, whether they really are scientifically important or not. Who knows? Because you never can really tell. And it's I think this is it. This is a travelogue. One of the most famous places that people may want to go to is Olympus Mons. That's a volcano. It's located in the Tharsis region. We'll see what that is. It is about the same size as the state of Arizona, to give you an idea of what its horizontal extent is. It's almost 3 times as tall above the ground or sea level as Mount Everest is. So this is a huge volcano. Well, that's nice. It says that for explorers to climb. I'm not so sure about that. Olympus Mons is located in the Tharsis region of Mars. We'll look at a map a little bit later. And the Tharsis region has not only this huge volcano or mountain, Olympus Mons, it has many very large volcanoes. Indicates here that the reason that volcanoes get so large is because Mars has a much weaker gravitational pull that allows the volcanoes to get bigger. Now, whatever is pushing them up meets less resistance on Mars than it would on Earth. Yeah, look at a better picture of this Marinus. This is essentially it's a Grand Canyon of Mars. Indicates what the size is. It's almost 2,000 miles long. Just think about Interstate 10 going from Jacksonville to Los Angeles or Santa Monica, California. It's about that length. It has a width of over 100 miles, which is sort of wider than the Panhandle of Florida. And it has it's very, very deep. So it has we'll look at this in more detail, another slide coming in. Something that was observed fairly early, even before all these missions, were the polar ice caps, the North and South Poles. The polar ice caps are formed by both frozen water or water ice and a frozen carbon dioxide, or what we call here dry ice. And the the dry ice is formed on the top. The water is more permanent. As we get into winter there, the atmosphere will actually freeze onto the poles, and of course, gets into the late spring, the frozen ice will not really evaporation, sublimation, back into the atmosphere. Now, while all this is going on, it's really affecting the climate, the winds, and other features in the Mars atmosphere. What's interesting about this Gale crater is that there's a strong suggestion that it was once home to some water. This before it's some volcanic eruptions. I really don't know. And here's a picture you saw already. Looks like I lost my PowerPoint. It'll take a second for me to get it back. Okay. Here's the Mars Grand Canyon, a little bit of pictures that we had in that the PowerPoint that we saw before. Again, it's 2,100 miles long, plus 120 miles wide, and 23,000 feet deep. Now the Grand Canyon, so it's 4 or 5 times as deep as the Grand Canyon, about 4 or 5, 6 times longer than the Grand Canyon, and several times wider than the Grand Canyon in the Southwest. Because there's a lot of dust on Mars, you'll find sand dunes, the picture of some sand dunes on the left picture, so sand dunes on the right. Is to look at see if I can find it. I don't know why this is not working. Anyhow, I'll just explain what this video is going to show. The photographs taken from Mars orbiters and landers indicated that there were some things that looked like stripes that were formed on Mars. A little bit like what you'd see if you went to the mountains on Earth, and after a few skiers have gone down, you see some things look like ski tracks going on all the way down to the bottom. Well, some of the scientists try to figure out what they were. If these were like objects that are kind of sliding down sand dunes, they would see basically an accumulation of stuff at the where these tracks ended. They didn't see that; it just sort of ended gradually, suddenly. There was not a whole lot of debris that was deposited at the end of these tracks. They're trying to figure out what it was. So they did some testing. They went out in the desert someplace and found a sand dune that was about the same slope as the dunes that are on Mars, about 30 degrees, I guess. They said, okay, what's going to happen? It had objects sliding down. Well, one thing they had sliding down were like plates of dry, slabs of dry ice. When the dry ice went down the slope, the dry ice has some weight, and as it went down the slope, the dry ice in contact with the slope would sublime, that it would turn to a gas, and then provide some lubrication. So what they noticed was that these little small sheets of dry ice would go sliding down the dune and until they actually ran into something, because this was done in the desert where they had some objects at the bottom, some bushes or trees or something down at the bottom. Let me try one more time, see if I can actually get this. Never mind. Okay, the Mars has polar ice caps, one at the North Pole, one at the South Pole. In 2004, they inferred that the polar caps were mostly water, with perhaps a meter of dry ice on top. They inferred that the polar dry ice is about 25% of the Mars atmosphere. This is important. Is this sufficient or insufficient for major climate change? Suppose that all that dry ice sublimed went into the atmosphere. Of course, that would increase the mass in the atmosphere or the surface pressure in the atmosphere by about 25%. Well, the surface pressure on Mars is less than 1% of the surface pressure on Earth. So adding an extra surface pressure about 25%, it's going to raise it, but it's not going to raise it to anything even close to what the Earth's atmosphere is. So one of the questions is, if there are more carbon dioxide in the atmosphere, would this cause climate change? Well, we know that carbon dioxide is a greenhouse gas. More carbon dioxide in the atmosphere would increase the temperature. I don't think it's going to increase the temperature by all that much unless there's a lot more dry ice or solid carbon dioxide on Mars than people have estimated so far. This is my guess. Other people have different opinions on this. It is very important to understand how much dry ice, how much solid carbon dioxide there is trapped in the North Pole and the South Pole in terms of future exploration. Okay, here's something we saw already. It's a different picture of Olympus Mons. Elevation of 72,000 feet compared to Mount Everest, which is less than 30,000 feet. You can see the different parts of it, the caldera, the escarpment, and the areole at the top of Olympus Mons. This is a picture you've seen already. This is the topography of part of Mars. On the left side, you'll see Olympus Mons is in the furthest northwest. That's right there. It's a single volcano. We have a set of volcanoes, three large volcanoes. In the west, it looks like Orion's belt. I'm sure it's not. Now, the question is, how are these formed? We'll look at this a little bit later. Also, this blue piece right here is the Hellas Basin is a very large basin. It's a remnant of, it's caused by an asteroid, large asteroid hitting Mars. And it turns out to be very important since it's a large hole. A large hole can hold a lot of dust, and people believe this is where the major dust storms originate, over at the Hellas Basin, which looks like it's just in the southern hemisphere, but not by very much. So anyway, there's Olympus Mons, there's the Hellas Basin, and here are some of the Tharsis. There's a Tharsis region over here. Those are Tharsis volcanoes. Okay, one of the questions that people have raised is, why does Mars have such large volcanoes, almost 3 times the size of the mountains and the volcanoes on Earth? It's a very short video. It's not even worth trying to find, I don't think. I think this is just, there we go. That doesn't seem to be working either. I'm sure I'm doing something wrong in trying to get the sound. Anyway, so one of the ideas is that on Earth, there are tectonic plates, and these tectonic plates move. And also there are some hot spots that come from the interior of the Earth. You can see the left picture. When you have like some islands are being formed, like Hawaiian Islands, other island chains, if they sit on top of a hot spot, then of course the magma is going to come up. It's going to push up the Earth and form a volcano. But meanwhile, the tectonic plate doesn't cause the whole plate to move. That is, the volcano is going to shift. In this case, it's shifting to the left. And eventually the volcano is going to move away from the hot spot and stop growing. And then another part of the plate is now over the hot spot, and that's going to cause a different mountain to form. So you see a whole sequence of mountains or volcanoes being formed on Earth. On Mars, there does not seem to be any tectonic plates. So what happens is that a particular volcano will sit over a hot spot and sit on it and sit on it and sit on it. It will not move. And that could cause the volcano to get larger and larger and larger. In addition, the lower gravity will allow the volcano also to get larger. Now, the atmosphere of Mars is about 95% to 96% carbon dioxide, and it gets cold up there, so there's going to be some dry ice at the poles and also some dry ice over the rest of Mars. Not very thick, because otherwise we would see the polar caps would cover the entire planet. And also there is some sun there. And this is a picture of dry ice on the surface under being sublimed or under sublimation. It's one of my favorite pictures because you can see some bare spots under the ice, and as the sun shines on it, the carbon dioxide will go into the atmosphere and go sublime, and you get these patterns People who sort of study some mathematics will probably recognize these, or biology recognize these as fractals or something, whatever you call them in various areas of science. They get these patterns forming on Mars that's due to the sublimation of the dry ice on the surface. So there are some interesting surface features. Also from it's a picture taken by an orbiter on Mars. You look down and there's very interesting patterns in the sand. I'm not sure what causes them, but it looks all this sort of layering patterns suggests that the geologic history on Mars is not very simple. It's probably complicated at different times when different layers were being deposited. This is a very famous result from a decade or so ago. The people, I think it's in Antarctica, found a meteorite, right? And they looked and realized that what's in the meteorite, the rock and the gases and so forth, were not consistent with what they would see on Earth. So it must have come from some other place. And then they believe it came from Mars, that a rock on Mars was maybe thrown up in the air, who knows, or hit by an asteroid. And it got down into Antarctica. One interesting thing about this is that there are two different isotopes of the gases when they actually analyze what was inside this rock. And that maybe Mars came from two different sources, not just from one place. It could have come from two different asteroids that collided, who knows. Anyhow, it's very interesting to think about what the history of Mars must have been like. Okay, we've looked at the surface features of Mars. We've looked at now it's going to look at the internal structure, which of course is not quite as easy, since even the rovers can't get down there. The belief is the following, and we'll talk a little bit about how people would even know about this. The inner core, about 1,000 miles in diameter, consists of iron, sulfur, and nickel. They have different densities, so it's possible to distinguish among them. The inner core is mostly solid, maybe a little bit of liquid component to it. If it's a liquid component, if it's like iron or nickel, would produce a magnetic field. But if it's just solid, you would not get a magnetic field from that. The next 1,000 or so miles, just outside of the inner core, this brownish region here, is mantle, mostly silicate. And then we have the cross structure, not unlike what we have on Earth, but the main difference is that the inner core is almost completely solid, whereas the inner core and the Earth has a significant part of it is a liquid, which causes our magnetic field. Because one question you probably have, and I had also, is how the heck do we know all this stuff? How do we know about that the Earth has a solid core, or what's in it? What kind of, we obviously no one has actually gone down there. And this is a result of the way people can do some data analysis. We usually think of an observation or an effect or something as having a cause and an effect. Something causes, and you measure the effect of it. Gravity causes a ball to drop, and the effect is the dropping of the ball. Well, if you know the cause, you can very easily use the laws of physics or chemistry or biology or whatever field you're in to determine what the effect is going to be. You just have to follow the laws. Unfortunately, this is not what usually happens. What you usually notice, we're doing especially experimental science, you see the effect. Now the question, what caused it? You have to go backwards. This is sometimes called an inverse problem, going in reverse. The effect is the observation, and now you're trying to infer what the cause is. This is very, very difficult to do. You have to work things backwards. This is something that I first encountered when I went to a Woodhull program when I was in graduate school, and they were looking at how one can infer the structure of the Earth on the basis of observations of the frequencies when earthquakes occur, or the other information they can get from the interior of the Earth, and kind of use those observations, use the laws of physics, and go backwards. This is very, very difficult to do. Also, it can be very unstable. That is, you can make a small mistake in the observation can lead to a major misunderstanding of what the actual cause was. Here are some examples. This is sometimes called remote sensing. This problem was certainly what they did on Mars, and they have to have some ways to sense information. Here's some examples. An MRI, you'd like to know what's in someone's head or what's in some part of someone's body, and you don't want to look at the effect directly, so use an MRI, and if you understand the physics of an MRI, you can actually go backwards and go from the effect, which is the image that you're getting, and determine what the actual structure is. Requires a lot of math and physics to do this, but that's the way things are now. Another example is the oil deposit. If you're looking in a place you expect there to be some oil, very difficult or very expensive to go down and actually look at it, so you can just create some sound waves and have the sound waves go down the oil deposit, look at what comes back. And so the oil deposit is really the cause, and the effect is what you see when the sound waves come back at you, and you have to then go backwards from the effect back to the cause. This is it's also called remote sensing. Calculating the structure of the Earth for measurements of seismic activity. This is what people have done, and presumably that's what they're doing on Mars also, the seismic activity, to try to infer what the structure of Mars is. Another example, and a counter example is, can you determine the shape of the Earth given the shadow on the moon? Well, this is how people inferred that the Earth was round, by looking at the shadow on the moon from an eclipse. Unfortunately, that can be a problem. If you assume that the Earth is a sphere, you can estimate how big the sphere is, but how do you know it's a sphere? It could be something else that's round, or other round things like cylinders and other shapes besides the sphere. So how do they even know it was a sphere? My guess is that they assumed that nature is beautiful, and that nature only deals with the most symmetric and simple objects. So once they knew once they assumed it was a sphere, they could infer where the shadow is. But sometimes that can be very difficult. Sometimes you're trying to do this backwards reasoning. More than one possibility can arise, and then you have to figure out which one is correct. More in the brain, your visual system. You have some visual information going into your brain, and the brain has to process it and tell you exactly what it is that you're seeing. Well, a very famous example, kind of a silly example in a way, is the following. Well, it's about 100 years ago, the question came up, can you hear the shape of a drum? If you hear a drum, can you infer what its shape is? Well, if you've seen drums before, so it's probably round, but it may not be. There are other shapes it could have had. And all you're given are the particular frequencies that the drum produces. So the question is, if you have two drums that produce exactly the same frequencies, high frequencies and low frequencies, all the different combinations, if the two drums appear to be identical based upon the effect or the output, can you infer that the drums have exactly the same shape? So this went unknown for what, I don't know, 50, 80 years, something like that. until someone determined, oh, they did find two drums that had different shapes, but produced exactly the same sound. So this tells you that just because when you try to go backwards, sometimes you may wind up with more than one answer, and you have to be very, very careful before you jump to conclusions. And so basically to determine the internal structure, people do things like this. Well, they're not really drums. Okay, let's look at the atmosphere of Mars next, but okay, let's do one more thing in the next 5 minutes, then we'll answer some questions. Mars has dust storms. It's pictured down below. This shows on 2 different dates. You see Mars before dust storm, and another 5 weeks later, I see that the picture of Mars looks quite different. Now, what causes the growth of dust storms? Well, Mars has some winds. It has winds are caused by pressure, by temperature and pressure differences. The wind will produce some dust. Dust gets up in the atmosphere. Well, up in the atmosphere, the sun's going to heat up the dust. Now, once you have more heating, it's going to increase the wind. And you have this kind of feedback mechanism. The wind produces the dust produces the heating increases the wind increases more dust, and so forth. And this process can have this like positive feedback and will result in a picture like we see in the lower right-hand corner. Now the dust is maintained in the atmosphere because of lack of rain. In other words, once the dust gets up there, it doesn't kind of rain out and then kind of cuts through this this feedback mechanism. Now, many of the dust storms originate in the Hellas Basin. We saw that before. And it's believed that it was formed 3 billion years ago, a long time, and when a large asteroid hit the surface of Mars. And also they've measured with instruments that the bottom of the crater can be warmer than the surface. And the important thing is that the crater is deeply filled with dust. There's a lot of dust around to produce a dust storm, and these dust storms can cover solar cells, as we found out. Okay, I said I have 8 minutes left. I better just quit now. But thanks for your attention today, and open your mics, ask questions, and or actually make comments, not just ask questions, because I don't know the answer, but just make comments, and thank you so much.
Just want to say thanks again. Thanks again. Really excellent. So much knowledge. So
I made it all.
Appreciate it.
Thank you, Steve.
Thank you.
George. Marilyn Frank, how are you?
I'm very good. How are you?
Okay.
Let me just ask you a personal question. What do you have pursued this just out of your own curiosity, right?
Yes, because Mars has been in the media for a long time, and I was very interested in physics and math and astronomy. So what really got me going in this is that after my first year at FSU, one of my colleagues went up to Cornell to visit with Carl Sagan, and he came back with, "Oh, we just have this model of what causes winds on Mars. Would you like to work with us?" And that really got me into really looking at all my depths. So I did work with my colleague and a little bit with Carl Sagan. I met him several times. And so knowing that someone that famous is sort of interested in what you're doing kind of gives you a little bit of encouragement. But,
Oh, for sure. Yeah. Great.
And my specialty at FSU is in geophysical fluid dynamics. And of course, there's fluids on Mars, and I guess it's sort of geophysical also, so that also helped.
Yeah, well, it's fascinating. Yeah, it's really good.
Thank you so much.